And up next, we have Lulamile Mzamo with the evaluation of heuristic guided character level world models for morphological segmentation of isiXhosa.
Thank you very much. The screen changes when one shares, so I hope everybody can see my screen. Okay, so my name is Lula. I'm doing work with Prof. Helberg and Prof. Sonia Bosch at UNISA. We're looking into unsupervised segmentation of isiXhosa. And in 2019, we presented introductory work on two unsupervised segmentation systems. One was called the Heuristics, maximum likelihood segmenter for isiXhosa. Another one was called the branching entropy segmenter for isiXhosa. In that work, we didn't really provide much evaluation information. In this work, we provide much more rigor in the work. So I will go through a bit of introduction on the language, then I'll talk to the heuristics that we use, and then I'll talk to the generation probability models that we use, and evaluation and conclusions, and maybe future work if I've got time. We're segmenting isiXhosa. isiXhosa is a resource-scarce language in the country, in South Africa. It is the second largest in the country, and it is an agglutinating language. Pretty much most of the Nguni languages in the country are agglutinating. And the Nguni languages in the country account for 45%, 5.8% of mother tongue speakers in the country. We use unsupervised machine learning because of scarcity of annotated data. The heuristics that we use for this work, we are looking at an isiXhosa word, and we're breaking it into pieces, right, into its morphemes. So we're making some heuristics. One is, if you find that the first letter is a vowel, make that a prefix morpheme. If the last letter is a vowel, also make that a morpheme into the suffix morpheme. Roots have got start with the consonant and end with the consonant, and prefix morphemes are syllables, full syllables, and the suffixes are reverse syllables. And that's how we use these heuristics. We use 4 generative models to model isiXhosa, and we test them and we compare them. The first one is called morpheme sequence, which is just we're saying that the statistical dependence between them is sequential. It's a sequential model. The independent affixes one says the prefix and the suffix are independent of each other, and they're independent of the root, but there's dependence of the morphemes within the affixes. The affix links mode says that there's dependence within an affix, but that the dependence with the root happens through the last suffix and the first prefix. That's how we associate it. And then circumfix links, we're saying that a prefix and a suffix actually combine into a circumfix, and that matters in the model. So that's the 4 models that we use. I will not go through each of them, but I don't know if I've got enough time for that, right? But for a morpheme sequence, that is how it would look, the actual segmentation. And you can see that if somebody knows isiXhosa, those are full syllables, and those will be reverse syllables. There are exceptions, of course, with an M in prefix and the W in a suffix when it is preceded by a vowel. So the one about independent affixes, we butcher the graphical modeling techniques such that we incorporate both hierarchical aspects to it and also dependency relations, and we separate that using dashes and full lines. And also in our modeling, we use recursion to just make the model easier. So it's the same model everywhere. In terms of evaluation, We used data for evaluation, we have to use two different sets of data to get rigor. Training data and testing data, it's preferred that they're separate. We combined text, and because it's unsupervised, it's unannotated, so we can pull just raw text. So there's work by Sneyman on gender classification. So we pulled his corpus of 1.3 million words. We combined that with the Constitution of South Africa, the isiXhosa version, and we scraped some Xhosa text off the internet, whatever we could find. We got about 31,000 words out of that. That gives us about 1.5 million words. For testing, we took work that I think it's Puttkamer and Iceland that they had done, where they were developing annotated data for 10 South African languages. So we took the Xhosa segmented, morphological analyzed work. So we took the results of that, and we take that as our testing corpus, right? And for setup, we try and do tenfold validation, in that we train with 10 different sets, but we evaluate with the same set. And because the work from Puttkamer and Iceland it used a morphological analyzer and a rule-based one, it doesn't provide, some of the analyses are not surface strict, let me put it that way. For example, if you segment the word Uganda and isiXhosa, a proper linguistic segmentation will be U, Ku, and the root will be under. But this does not, if you concatenate those, they don't form into Uganda because of the W that gets formed in that exercise. Right, so we have to cater for that. So we have to take those out, because that's not what we are testing in the exercise. We evaluated against a random segmenter, which just says this location is, it says randomly that this location is a segment boundary. Also evaluated against Morphesa baseline and our previous work on the branching entropy that we presented last year. And we are using boundary, morpheme bound identification accuracy in F1 score as our evaluation metric. And in the work, we did some statistical significance testing. Results and on a peak scores for each system are shown here. In the work that we presented last year, Morphesa baseline and XBES on the accuracy were comparable, but the branching entropy system XBES provided a higher F1 score. In this work, which is the heuristic Mzamo likelihood segmenter, all of the modes that we used could not get the same accuracy, could not get a good accuracy. So the best is the independent affixes with 75.2%, and that is followed by the morpheme sequence model. So in terms of if one is looking for an unsupervised benchmark, Morphesa baseline and the branching entropy segmenter are still the benchmarks on accuracy. But if one then moves into look at the F1 score, which is a different metric, and it penalizes for negatives, you find that the morpheme sequence model and the independent affixes model actually do a good job, and they are comparable in terms of the sense of statistical significance. So they do better than the other two. So that is the results that we get in terms of these scores. If you look at trending, of interest for us is the independent affixes model, in that it starts with a high accuracy of about 70%, and it starts with that accuracy from very low training set side, 100, right? And it continues to stay high, even though it then degrades a little bit. That's on accuracy. And you see that the independent affixes model also in F1 score is comparable for for small training set sizes, even though the branching entropy beats it fair and square. That is the F1 score trend. Our conclusions are that we believe that our work is contributing to the unsupervised word segmentation work. We contribute these models, and we provide a system that provides superior F1 scores to what we've done so far. We also checked for smoothing effect, and if one goes back, you can see that of the models that we use, smoothing is useful on 3 of them, and it's useful for both the accuracy and F1 score, but it's not useful for the independent affixes model, right? So that's what we get. So that is my presentation, and I hope I didn't take too much time. Oh, sorry, going forward, our intention is to use this work for other languages. For example, there's 3 more Nguni languages that could be checked on this, so we're going to go into that. And also, it will be interesting to see what the heuristics of the other languages in South Africa actually have, and maybe we can piggyback on that. And also, we know that segmentation does improve web embeddings for agglutinating languages, and so we're hoping to use this work as a pipeline towards other processing works like machine translation, etc. Okay, I hope everybody understood that. It went by in a blaze, and I'm done. Thank you.
Thank you very much.